Okay, so we will continue on our last lectures, okay, about a single phase AC controller, okay. Yeah, I believe we have done this in the class, and we verified that the equations here, okay, is correct, okay, in order to get the voltage magnitude, okay, to control the voltage magnitude. Okay, now before we move on, right, so there is another thing I need to stress out is that, this what we call this pulse generator, right? Okay, because we know that the supply, okay, phase is start from 0 degree, so it's pretty easy for us to actually control it. And in real AC, right, we may not know, okay, the phase is not necessarily start from 0, right? It starts from the moment you connect to it. So how do we solve this problem? Okay, so we need again a thing called PLL. Remember in the DC to AC, how do we know that the sine wave generated by the inverter actually can synchronize with the grid sine wave? Okay, so similarly, for this pulse to be able to control this, right, you must be synchronized with the AC. Remember, if you deal with AC, right, okay, and there are synchronization, you have to make sure that you use a PLL. Of course, this is an experimental, right? I mean, in real circuit, you cannot just do like that. You cannot just put an AC and your pulse are there. It will never synchronize, okay? So to solve that problem, right, you just need to, okay, I show one example here in MATLAB, okay? Right. So you can see, okay, I actually make it a blocks already for the AC controller, and the angle is pi divided by 3. So when you look into it, okay, again, okay, these are our triangle, okay, and then we have this controller inside here, all right, and this controller, okay, will output the pulse, okay, will output the pulse. And then this one, when you look inside, right, there is a PLL. See, there's a PLL here. The job of the PLL is to synchronize, okay, the sine wave. All right. So in real application, if you really want to do this hardware, right, you need to have this PLL to be programmed into your Arduino, in other words. Okay, so programming method is exactly the same as long as you know how to make this block works, you can actually program into Arduino. All right. The detail of programming Arduino, we'll see how first. If we have enough time, maybe the last class I will go through it. Okay. So this will just show you another examples that run it. And then we should be able to to actually chop off the sine wave lah. Okay, so even though from the source here, okay, now there is a phase shift, right? Let's say I phase shift it to 30 degree. Okay, 30 degree. Okay, so we'll be able to, you see the first round, it won't be cut properly because the phase lock loop is taking time, right? Slowly, you can see it will synchronize. Yeah, this is what's going to happen from time to time. You hear this. Okay, you want to see how the synchronize work properly, you may need to increase the time. to 0.1 second, for example. Huh? Okay, now you can see at this point it's already synchronized. And of course, you will see that because we measure the whole thing here, right? It will affect your output, but in the real circuit, right? You should get the, 180 something, nearly 200, not 100, around 200 something, okay, which is this part because the PLL will need time to synchronize. So that is for practical hardware, okay. If you want to do a hardware, please make sure that you have to include the PLL lah. And of course, this is just one of the way lah. You can use other way as well, okay. I'm not sure what are the best way lah. Okay, this is one of the way. Okay, a bit complicated, but never mind. Just to show you the concept that the importance of the PLL here. Okay, so now what if we, like the old one we did here. Okay. Okay, this is the old one. Okay, so okay, now the old one normal, under normal condition, we can actually run it again here. Let's say. Okay, and then we change this. Because we know here, theory, idea, we know it's always start from 0. But remember, in actual AC, you will never start with 0. You can start with any angle, depend on the moment you turn it on. Okay? So now you see what happened is when you don't have So when you don't have the PLL, okay, so you will see that you are actually, changing the the 30 degree, you have to minus the 30 degree. So your firing angle, right, will not be correct, okay, if you do not have the PLL thing, okay? If you don't have the PLL, it will affect your firing angle accuracy lah. Okay, for example, you want to fire at 30 degree, and if the sine wave start at 30 degree, is 30 minus 30, it becomes 0. So you literally does not have any firing angle control. All right, so that is actually what happening, when you don't have the PLL. Let's say this one is what? Oh, it's 45 degree. Okay, let's say 545. Or minus 45, I forget already. Then it become either it become 90 or yeah, it become 90. It's 45 plus 45, you see? It become 90. But what you want is 45. Without PLL, right? That is what happening. And every time you turn it on, you get different firing angle. Now, if we change this to negative 45, there's no chopping at all. Okay, because the firing angle and the phase shift cancel out each other. Okay, so it's like, of course, in theory, the understanding, okay, this one is fine. But remember, when you really want to make the real circuit in hardware, this is something you need to consider. Okay, yeah. So like I say lah, usually I change this assignment every year, and then when they are dealing with hardware, I will usually talk about this in more detail, how to make PLL into the hardware and so forth. Okay. So here we'll just let you know that the importance of PLL, but for theoretical, then should be fine. All right. And then, so up to this point, any questions?
No questions.
Okay. Okay, now we move on to one of these example, class example. So, okay, so tell you that a full wave AC controller have a resistive load of 10 ohm. The input voltage 120-60 hertz. Okay, this one is from the textbook, and textbook is American written, so they follow American. So the delay angle for T1, T2 equals to pi divided by 2, which is 90 degree. Then determine the RMS. Okay, so equation very straightforward, like I said. Okay, if you punch it correctly, right, you should get this. Okay, if you punch it wrongly, then you get some other result. So this is one of the way how your final will look like. And then very important, okay, is that because of the sine is no longer sine wave, first thing, okay, your output. So obviously you have two things happen. One is you will have a very high harmonic, okay. Second is what comes together with harmonics is the power factor. Okay, so in this case, to your load, right, like I said, okay, low power is okay, low power stuff is still okay, resistive load, heating device, magnetic coil, all this is okay. But for motor, you have to be very careful, especially AC motor. DC is still okay, but AC motor, you will actually, because of high harmonic, high power factor. Okay, like I said, for LV, single phase is also not a big issue, but LV three phase, you will have a very serious power factor issue. So how to calculate the power factor? Okay, that is, okay, first of all, we need to calculate the current. Okay, the output current. The output current will be, okay, will be the output voltage divided by resistive load. So you get the output current is 8.4 amp. And then the output power, okay, the output power is I square R. Okay, I square R. Okay, then you get, this is your output power. Okay, this is your output power. And then after that, okay, we need to calculate the input, okay, power. As we know that input current is the same, right? It's a series circuit. So the VA, apparent power, okay, rating will be the VS, okay, multiplied by the IO, because the current will be the same in series. So you will get 1018, okay, VA. And then we will divide, okay, we use the output, the real power divided by the apparent power, okay, then you will get a power factor of 0.707. Okay, so this is how you calculate. You can see that when you do that, right, it immediately affects your power factor. Okay, so why there is not so concerned when you use it in your house? I said for single phase LV, right? TMV actually not really look into this power factor issue, But in three-phase system, if your house bungalow usually, or the what we call the shop, okay, that you are taking in any shop lot, shop houses, you are taking three-phase, okay, then TMB will charge you penalty, because TMB will start to charge you if your power factor is lower than this 85. Okay, now of course, based on my experience, those big corporation, like UCSI, those are when they hire consultant, the consultant will tell them, you need to put cap bank or else you gonna the charges. But the thing is that a lot of these small business owner, especially those short lot, they usually don't hire professional consultant, right? They just call the, electrical people to contractor to just, I want to add this, I want to add this, then they will just connect for that. Especially they have a light dimmer system, to control the lighting. So what happened is that they will end up with a, like this one, okay, very low. And every month they kena penalty, they also didn't realize, okay, because the contractor just say, oh, you want dimmer for all your restaurant light, can, he just connect for you, right? It's not his responsible to tell you you will get all this, okay? And then there is.
Rodney,
Yes.
Sorry for the interrupt, right? I think there's an issue with some student cannot They cannot get into the team. You can see the refer to the chat there.
Oh, wait, cannot get to the team. Interesting. Why? I mean, get them the code should be able, right? Okay, wow. I can hear and see the slide. Okay. Okay, well, okay. What is happening? Okay, can you see my chat? Something is weird. Apparently class is on and it's like, but I can't see or hear anything. Now can hear or not? Some students cannot listen, but they can type.
So maybe you can type in the chat because they cannot access here. So whatever you say, so they cannot hear.
Oh.
Maybe type in the chat.
Maybe ask them to. Let me see.
I think some of the class have the issue also. So what they do, right? We need to invite them. They only can enter because the why there are only 40 people there, right? Is because there are some people who would late to join the team, right? We automatically cannot see the teams.
Cannot lah. You see, we got 80 people here.
But it's supposed to be 100 something, right?
Yeah. Supposed to be 100 something. Yeah. Let's see.
The 14 is the extra day. I think someone opened up the meeting room so they join it, and then inside there nothing. Maybe.
Again, I told them already, right? Not to simply open by their own. I think this group of people going to the wrong room, right? Let me check again.
You can invite them to this.
Hey, no, it's still in the same room.
Because this actually happened on the recent MS Team also, not only this class. I think other class also.
Really?
I think I have tourism class last time, and I was late 30 minutes, and I enter right. I cannot see the join button interface there, the meeting room joining interface.
Oh.
And I was wondering, is it me late for the class, so they block me or this and that? So apparently,
okay, just maybe let me know their name first. Let me know your yeah. I think UCSI may be doing something to stop you guys from coming late lah. So online also late, man. You guys, come on, You know, online is the best place. You know, come in, log on, you can go and sleep, or nobody care. I need to. Okay. So Fu Tan Kai Hong. Wow, interesting. Tan Kai Hong has to go one by one.
Maybe can go to the participant there and then below see who haven't joined this meeting. Participant, yeah, there's a participant there.
Show participant.
They will show you the list who actually not here yet.
Oh, but I think they have this one we call show more thing. Oh my God, this is going to take at least half an hour. Okay, let me try to see full. Wow, it's all alphabetic leh. Okay, maybe I can type here to get their name. Ryan has put on a meeting link chat. You all try see can get in or not? In the chat box. You all try see you can get in or not? Same problem. Okay. Fu Tun Hao is in this meeting, and then wow. So make an attendee. Okay. So let me try.
Actually, not only lecturer can invite the student. If your friend is not here, you can actually invite them also.
Oh, okay, guys. Then please have a friend. If I'm going to do that, it's going to be long. Not in this meeting. So many of. So, wow. Why suddenly they do something like that? Must be someone is causing problem. The UCSI team experience. If it's a white bug, then nothing we can do lah, right? Hey, Futun, how I already add you still cannot. Participant. Oh, how finds out also. Okay. We are not informed this is going to happen. Okay, so I also don't know what to do. If like that lah. Let's see. 115. How am I going to know you are in the meeting or not? Can anyone tell me? How do I invite them? I only see the role. I can only add member, but I really don't know how to invite you guys. Someone started to? No, I don't think so. Perhaps we should take a class. Kick out from the room. Yeah, I'm the one who started the meeting, so so far it's only one meeting here, so I don't think it's a two meeting problem. Okay, the class number increased to 91 already. Okay. Okay, I can hear some noises. Ate, can you show me how to invite them?
Okay, I share my screen already.
Okay, I have difficulties on this.
You can see my screen right now, right?
Okay, yes.
Yeah, so apparently I press here to show participant.
Okay.
Yeah. If they are actually not enter, right, some of them you can check from here. Others from the chat.
Others from the chat. Okay. Mavi Singh. Okay.
Some of them actually you need to type the name here.
Okay.
And then you like just now the right? Kim Han, right? Yeah. So like this, right? So
their name will appear.
I think he's already in. So if the one is not in, right, you can just press request to join.
Request to join.
Yeah. For those who not in.
But just now I moved to certain people name, there is no request to join button for me to press.
Because they are in the meeting room already.
Oh, okay. Yeah. Okay, let me try again now. In this case, I can see there are quite a number of students already in here. Okay, Muhammad Al Faiza. Let me try that. See, I can. Quest control. What should I do? Okay. Hey, Marvin Singh Gill, I think just now, yeah, Tae Boon Hong invited you already. How come you still say you cannot? Okay. Okay. Muhammad. Okay. Okay. Wow. Some students, they are not in our Power E class, but there are so many names that request to join. $96 already inside this. Okay, now can hear already. So I'm still not in the correct. You are in the correct meeting. It's just something is very wrong somewhere in team. I don't know whether it's bug or not. Okay. Okay, Marvin Singh. Just now it has been added, but still. Okay. Request to join. Okay. We had 99 students already. Marvinjit Singh, can you hear me? I just added you. Okay, I think for now, for those who still cannot hear, maybe you all leave and ask your friend to invite you all. Okay or not? Okay. Okay, yeah, we have wasted some time on this already. Hopefully this is a temporary problem. If this happen again, means that UCSI may, we subscribe 360, you know, they have full control. If they want to set after half an hour, you all cannot join means cannot join. All right. All right. So yeah. So again, please don't be late lah. Okay. Especially big class like that, if the whole class only 10 students, easy to settle. Now, you know, 99. Okay. All right. So where am I? Oh, okay. Power factor. All right. Like I said, if you are using this AC controller, that will actually distort the sinusoidal waveform, okay, of the output, right? You eventually need to be aware of two power quality issue. Okay, one of them is the power factor, another one is the harmonics. Okay, like for a single phase load, right? Usually they are very low power. Okay, so it shouldn't be any big issue. All right. And like I said, yeah, please try this at home. Okay, for Malaysia voltage, and then a different firing angle, then you may have a different, you know, answer here. Okay, now we move on to the second examples. Now we know that we need two thyristor. Okay, we need the two thyristor. Okay, here in order to do the what we call this AC controller. So it can be done so, okay, by using this, okay, topologies. Okay, now what you need to do is that you just need to require, instead of two, right, you just require to have only one thyristor, only one single thyristor, okay, work together with 4 diodes, okay, or with a MOSFET. Okay, now with MOSFET, they operate differently. Okay, of course, with MOSFET, it acts as an AC switches. Okay, it acts as a AC switches. And then, of course, the controller here will be very much different compared to the thyristor. Okay, now we just focus on thyristor now. So in this case, you save one thyristor, okay, especially for high power application, thyristor is getting expensive as the power, current and voltage increases, right? And for those who are using this low power, it doesn't matter lah. Okay, so this is just to show you that there is another way of constructing, okay, this AC controller using only one thyristor. So we can actually do that, okay, by, you know, using this, you know, you can actually test it out. Okay, you can actually test it out. Let's see. Okay. Okay, to make it easy, maybe we'll use this one example. All right. So what you guys need to do is just need to modify this part. Okay. You just need to put one this thyristor. Okay, firing angle can be the same. And then we have a thyristor, and you just put 4 diodes here. The rest, okay, is the same. Okay, you know, 3 to 5, right? 50 hertz. Okay, this one is also the same. Okay, pi divided by 4, no change. You just change this part only. Load supposedly should be the same, 100 ohms. Okay, 10 ohms. And then if everything works correctly, okay, and yeah, it will have the same result. Okay, you will have the same result. All right. Okay, let's say yeah, if I divide it by 3, you can see much more clear lah, huh? Divided by 3, and I run this again. Okay, so this is just another alternative way, okay, of doing this AC controller. Okay, so meanwhile, okay, can you guys do this and show me the chat box? And at the same time here, I'm going to see whoever I can I can, yeah, invite again. All right, please do this. Okay. Ryan, you are using a wrong model. That model is you are looking at is a solid state relay. It's not the AC controller. Okay. That one I'll explain after this one. Okay, please do this one first. Okay, the one I show in the share screen. Okay, you can you guys just simple change. You should be able to do it. Okay, anyone need invitation? Maybe you just type in the chat box while I'm waiting. Yeah, for you guys to show the Simulink. Okay, finally we have one come out already. Tan Kai Hong, very good. Okay. Yeah, you will notice the result may be a bit slightly different, okay, compared to the one that we use thyristor, the 2-thyristor or triac lah. That is simply because, okay, there are voltage drop across these 4 diodes. All right. So it's it's about cost and performance lah. All right. Using 1 thyristor is obviously much more cheaper than using 2, especially the high power one. They don't have this triac for high power. You need to do this, to use 2 thyristor to combine them. High power means that, high power applications, okay, a few thousand, watt and above lah. It shouldn't have any difference as long as if your source is 60 hertz, right? Your pulse generator need to be 120 hertz. If you use 50 hertz again, it will still, it will happen just like what happening I show you when the phase is out of sync. You will have the out of sync problem. Yeah, they are different, of course. But now, like I said, nowadays, right, those advanced AC controller, they come with PLL. So the PLL will actually track the frequencies. Okay, the first job is to track the frequency and then track the phase. Then you shouldn't have any issue lah for the new PLL.
So can I cross-check with you the pulse generator parameter?
Oh, okay. Yeah. These are the yeah, just now was 4 lah. I changed to 3. So it should be more or less the same like the one that you use for the 2 thyristor. Okay.
So for the thyristor, did we do any changes on thyristor parameter?
No, we just no change at all. No change.
Okay. So other than the pulse, right? So only the pulse will change the function.
Pulse actually no change except the delay lah, right? Depend on which firing angle you are talking about, ma. And of course, if you change to 60 hertz, this one you need to change 60 hertz, or else it will calculate wrongly. Your RMS will be different. So if you want to see whether this thing is really firing correctly, very simple. You just make the scope, okay, into 2 scope lah. Then you see the pulse and the scope. Then you can see much more clearly. Then you change this to 2, right? Okay, for example, you change this one into 2. Yeah, usually I will do that lah. Okay, then maybe the top one okay, here, and then you run. Okay, then you can see, okay, it should cut, at the, what we call this, yeah, the angle lah.
So if my one only cut in the half, leh?
You want cut half, it's 90 degree.
Oh, because in my chat a bit weird in my, I posted in the chat box there.
Oh. Wait. How come your one so strange one?
Oh, yeah.
Table Hong, right?
Yeah, correct.
Wait. You see, I half half one. Oh. Let's see. Is your diagram wrong? Table Hong. Let's see others. 5, 7. Okay. The rest. Okay. Table Hong. Check. Okay. Your diode. Are you using the simple diode?
I'm using. I know the problem.
Okay, I can't hear you just now. It was so noisy. Okay, what's that?
My wire I put wrongly.
Yeah, you see.
Sorry.
No. That's why I usually don't do troubleshoot for students. You know, if the one I show you can work, and some other student they prove it can work, you know, that means something wrong on your side already lah. Okay. Wow, Sir Chan Hong, you still can do simulation. Oh, very encouraging. Okay. Okay, Table Hong finally. Okay lah. So, all right. So that should be able to conclude our, what we call this, our testing here. Okay. Wow, what is this again? Generator phase delay. Ryan, why your thing always cannot work properly one? That really, you don't go simply and change something that you're not supposed to change. Okay. If you do that, right, every time I notice your problem is that you go and change something that you're not supposed to change. Then of course thing won't work lah, right? So you see carefully what's the difference between yours and mine. You go and your hand are so itchy, you know. You go and change the time base to simulation base. Of course it don't work. And the period is 100, you put 200. So if you keep on doing So if you keep on doing that way, I will not entertain you anymore, all right? So please don't do that, okay? But I think the whole class only Ryan would like to do that, okay? So you see, Ryan, when you put this thing on, right, it will not be simulation based by default. Okay, if you don't go and change it, see, by default, if you're not going to change it, it's this one. So I don't know why every time you ask me why you cannot work. I noticed this already. I just don't want to tell you because you're so, you know, I don't know. Okay, so please don't go and tangan itchy. I don't know what is your intention to do that, or you want to test whether Dr. Rodney can spot your error or not. Okay lah, I surrender lah. You don't test me that way. I sure feel lah. Oh, I hope that will make you happy. So my intention here is that please follow the thing properly. This is not the first time already. Since the very first day you told me, sir, why cannot? I already noticed that. You go and change something, that's not supposed to change. Like even you drag here, you don't change it, it won't change, okay? All right. So if it is unintentional, that is fine. Okay, I will help you to look into it. But every time, you know, that's the problem. I notice every time this is happening. So Ryan, if you really want me to help you to look into it, please make sure that you don't tangan itchy and change the thing and mess up the thing. Yeah, I don't know your intention, but some students in the past really do that for one intention. They want to test, see Dr. Ronnie really know MATLAB or not. Then I surrender, lor. Because MATLAB was so big, I don't dare to say that I'm good in MATLAB even until today. Okay, so if that makes you happy, then yeah, please don't do that again. All right, let's move on. Okay, so where is the application of this, you know, this thing, okay? So obviously I told you guys before, okay, yeah, what we call this a dimmer, all right? So one of the very common application, yeah. Nowadays, of course, we no longer use light bulb, okay? So, you know, we use LED lighting. And of course, use LED lighting, you need to have a dimmable driver, you need to have this. So it's basically a AC to DC and DC to DC converter. So the AC to DC is here, AC to DC. Okay, so the DC is very high, right? Then you will need to have a DC-DC converter. Okay, DC-DC converter. So it's a two-stage. When you see this driver nowadays used in the market, it's always a two-stage, you know, converter to actually, you know, control the brightness of the light. All right. Okay. Now the next example is that, okay, you will realize that this is the one that I use what we call a transistor, okay? So usually the one that is used in transistor is always applied on the MOSFET solid state, okay, relay. So which will allow the AC to pass through without cutting them, okay, like the one, the phase angle, it just acts as a relay or a AC switch, okay, AC switch, all right? So this is one of the example, okay, you can actually try to download this one. It will show the AC switch. Let me see if we have one here myself or not. Okay, sometime solid state relay, solid state relay. Oh, it's not here. Solid state relay, MOSFET solid state relay. Where is it? Where is it? Transfer characteristic. I think I made this many years ago. So that is not here. Let me just find solid state relay. Solid state relay. Okay. So different application, I will say. Solid state relay also can control, but the control is not so straightforward like the one we use in this, what we call this AC controller, okay? Okay. Okay. So what happened is that you can see that I just fully turn on, turn off, and turn on again. Okay, so it just acts as an AC switch off. It turn on, it allows full AC to go through, turn off totally, block off the AC, and turn on again. It's just like a mechanical relay, but it is electronic. You don't see electromagnetic coil there. You don't see any mechanical moving parts. Okay, so this is a signal I put in. Okay, you just basically turn on and off only. Okay, you turn on the transistor, you allow all the current to flow through the AC lah. Okay, and then you turn off to 0, then you off the relay and you turn on again. Okay, then you will allow the AC to pass through. There is no like cutting thing. If you want to cut, it will be much more complicated, but usually in real application, right? If you are doing the solid state relay you're using, if you want to control the voltage, okay, you will use the thyristor. Okay, so this one you can download. Okay, you can download from the file exchange here. Okay, and play around with it lah. You can just simply change this signal generator. Okay, to actually change the the time lah. Okay, you can just move around. Yeah. I think you can change the time here. If not, I can change the time here. Okay, to move them around. Like if I change this to 0.2, okay, then you can change this. Then you can change this one, okay, to 0.2. Okay, then it will change the time. Okay, it will change the time, and then okay, if it's changed already, I think we need to save it. Okay, and then yeah, you run it again. And then it will on a little bit longer until 0.2 seconds. Oh, so okay, so these are the two. Yeah, so that's mean circuit with 4 diode, right? You use a MOSFET, usually used for relay, and those either use it for thyristor can be used for this, light dimmer. This is a solid state relay, how it looks like lah. Okay, you can see solid state relay. So it's 2 in, 2 out. Some they look something like that. Okay, some they look something like that. And then in normal application, they also use like, a thyristor. Okay, so again, this is also for high power applications, solid state relay. Okay, there's also AC controller. It's part of the AC controller lah. Okay, I think we have done about single phase. Any question before we move on?
No, sir.
Okay, all right. So now let's move on to 3-phase. Now 3-phase is literally just a copy of the other, the thyristor set into 3 set lah. Okay, so as we know that, right? This is 1 set. Okay, 1 set of thyristor set, second set of a thyristor. You just copy another 2 set, and of course you have 3-phase supply that you go through. Again, 3-phase mean you need to have a 3-phase load. You cannot use a 3-phase controller just to control a single phase. You will end up with voltage unbalanced. Okay, you will end up with unbalanced, and then unbalanced leads to a lot of problems lah. Okay, so now there is one thing you need to know that, right, is the controller part. Okay, the controller part, it won't be as straightforward as the one we do in the single phase. Okay, now the controller part, because it's 3-phase, okay, phase different in 120 degree, and this is the time where we need to have this what we call this phase lock loop. Okay, to make sure that especially 3-phase, you have to lock them correctly. Okay, so that you can track them. And then the controller, like you will see, T1 It's not T2, right? It's 4. And 3 is not 4, right? It's 6. So you can see these are the order of the controller, okay, for these 3 phase. Now, for theoretical part, okay, like I said, it is governed by 3 different equations, not a single equation like we use in the single phase. Okay, the output voltage equation, okay, is depend on your firing angle, okay, between 0 to 60, okay, you will use this equation, okay, 61, 90, you will use this equation, okay, and then 91 to 150, you will use these equations, okay. So that means the highest angle you can go, right, is actually up to 150. And usually, we don't go up to that high because the voltage will be very, very much distorted. Okay, but theoretically, we can go up to 150. So just again, okay, you need to calculate this, make sure you punch it correctly in your calculator. And again, I stress that when you see pi, right, make sure that you set your calculator into radian mode, or else you will get the wrong answer without noticing it. It's just wrong because, you know, yeah. Okay. Now, all right. So there is, okay, these are some of the examples, okay, of the 3 phase, okay, what we call this AC controller, 10 ohm, line to line input voltage, okay, and then line, okay, again, this is from the American textbook, okay, so we got 208, okay, RMS, and then 60 hertz, and delay firing angle is 1/3, okay, and determine the RMS output voltage and the power factor, okay. So first of all, okay, we need to find the phase voltage, okay, the phase voltage. So you must know how you have to divide the line voltage to square root of 3. So for Malaysia, right, Malaysia is 415, okay, Malaysia is 415. In the exam, I usually use back Malaysia system, okay. Okay, and divided by 3 lah. So you will get 240. Okay, unless I put 400 watt. Okay, if I put 400 watt, then you will end up with 230. So the VS, you just need to substitute in here. And of course, the angle here, you just need to substitute into the alpha. Alpha, if everything is correct, right, you should get this number. Okay, you should get this number if everything is correct. And then similarly, okay, to calculate the power factors, okay, we need to calculate the, okay, this one is the phase, one of the phase only. So, okay, the current, okay, voltage divided by R, you got 10 amp. Okay, and then right now you're going to have this power output, right? But now it's 3 phase. So power output of 3 phase, you need to multiply by 3. Okay, multiply by 3. All right, so your 3 phase will have 3000, right? And then, like I said, the current will be the same because it's in series, and the VA apparent power, okay, is your VS, and then multiply by 3 again, you will have 3006. And then a power factor is real power divided by the apparent power, you will have a 0.84. Okay, slightly lower than the TMV limit, all right, but it's become like a bit higher compared to the what we call this single phase. Okay, so that is the, of course, this equation changes if my, you know, the angle change lah. All right, so you must know which equations to put in. For your information in your final exam, I will not give equations, so you just need to memorize it lah, for these 3 equations. Okay, up to this point, any questions? Hello, class?
No.
Okay. All right, so now we move on, okay, to the simulation here, okay. Okay, we have a three-phase source, okay, and then we split it up into three phases. Okay, so we will have these all three set of the thyristor set here. Okay, 1, 2, 3, and each of them connected to the load here, 3 load again, and each of them we have a voltage measurement. Okay, each of them we have a voltage measurement. You can see that each of the output will have a voltage measurement. And then, okay, we will have this measurement of the voltage. This one is the voltage measurement blocks. Okay, so it go into the PLL. Okay, it go into the PLL. All right, again, this one is pi over 3. And there is a block called thyristor 6-pulse generator. Okay, thyristor 6-pulse generator, okay, is designed to actually, okay, pulse all these three in the correct timing. And the output of the pulse, right, yeah, is 1. Obviously, we know the 1 volt will not be activated. So we increase it to 10 watt or 12 volt. And we have to split, okay, the pulse signal into the separate, okay, 6 line, okay, into separate 6 line. And all these line, okay, are properly, okay, what we call align in the way that, you know, the first one, second one, okay, for the top, all right, and the third and the fourth for the middle, okay, and the fifth and the sixth one for the last one. Remember, you have to make this correctly. It follow the direction. Okay, when this is going to this direction, it will be the second line. 2 or the even line. 2, 4, 6. Okay, just like 2, 4, 6. Okay, so these are the okay, the setup, okay, of this. I don't think you guys want to do it, okay, but I will show a demo later. Okay, now come to the PLL. Okay, so if everything is correct, okay, so this will be your sine wave, the 3-phase, and this will be the output pulse, okay, of the what we call thyristor generator. Okay, it will generate this generator, okay, and then you will notice that there is one thing you need to change, the initial input, that is the phase angle. This one you need to change to 30. Originally, okay, it is 0. All right, let me show you the original one. Okay, 0. Okay, see. Three-phase AC. Okay, so this is the one I did, and then okay. So if you look at the PLL blocks, okay, control. Oh, it should be in the specialized power already. PLL blocks, okay. So if you notice, same applicable to this single phase. If you know the starting angle is different. Okay, you see, by default, right, if I don't make any changes, it starts with 0. Okay, it starts with 0 and 60 hertz. And then why I need to change it to 30 to 50? Okay, obviously 50 you all understand because our frequency is 50 Hertz. Why 30? Okay, because the sine wave here, see at this point, it starts at 30 degree. You see in this AC three phase, right? Waveform, right? It never start at 0. Okay, when the generator run, right? You can see at the yellow phase, it's actually start, okay, at 30 degree. Okay, so yeah, so you have to set them correctly, okay, in the PLL so that it can track, you know, much more accurately lah. Okay, so that is the output, okay, of for each of the phase, okay, because each of them, right, we will have the output. So for three phases, this is how it looks like. Okay, this is how it looks like. Okay, you can see at this point, right, it actually cut from here. And then the second one is actually cut from here, the blue phase. Okay. So these two contribute to one of the phase output. All right. And then similarly, okay, this is another phase, right? Okay, it contribute, okay, to one of the output. Okay, different by 30 degree. So this will be the output of your three phase. Of course, obviously, again, it's very distorted, super high harmonic. Okay, but for a heating load or resistive load, right, it's not a problem. So if we test this model here, so don't worry, I won't ask you guys to do it. But you want to do it at home also can, because the parameter, the only parameter you need to take care is in these blocks. The rest, you know, is this block. The rest, you know, nothing much. Okay. Okay, so that is, you know, how the, yeah, AC for three phase. Okay. So you want to test it, you can test, I think, yeah, this block important, okay, to make sure this one is changed. And then the rest you don't kacau lah, okay. And this one, okay, if I'm not mistaken, I didn't do any changes. Okay, this is the pulse width lah, okay, so I didn't do any changes because this is the just like a pulse generator, but it's designed for three phase, okay, to actually connect them. And from here, you can actually see the pulse output lah. And you can see the pulse output, okay, which I already show in the slide, okay, the pulse output. And of course, you can change a bit, you know, of this divided by 4, divided by 3, then you see the difference of the, of course, this is RMS to calculate just one of the phase output. Yeah, the lower the firing angle, the higher the wattage. Okay, so it looks something like that. Again, very much distorted. All right. Okay, so yeah. So don't worry, I don't expect you all do this in the class. Okay, it's going to be going to take a longer time. Okay, but the most important is to make sure that you know how to use the equation and you can verify it here. Okay. All right, where is this, what we call this application? Okay, the application of this, right, is actually for AC motor soft starter. Okay, now, soft starter means that, okay, if you don't have any soft starter, the moment you turn on the motor, what happens? Inrush current will come in. Okay, you will have a lot of inrush current, and if your protection, especially the MCV part, if you are not designed well, it will trip. So every time you start the motor, it trips. So what happened? It's a dead loop, right? You can never start the motor, right? Because of the wrong sizing of it. And one of the way to solve this problem is that they will introduce a product called soft starter. What the soft starter did is that when the moment you start, right, it actually firing at a very high firing angle so that your wattage, okay, the RMS voltage is reduced. Okay, and then when you reduce, right, your voltage reduce, your current reduce, and then slowly, okay, usually less than 1 second or 2 seconds, it slowly increase, okay, the voltage back to its normal. So you don't need to worry about spoiling your motor because it's not run your motor at, like for example, at pi/3 all the time. If you do that, right, high harmonic to your more inductive load is going to damage your motor by overheating it. So you will not overheating it because it is just, during a starting time, okay? It's during a starting time. So you will see that, yeah, these are one of the, oh, okay, so these are the graph, okay, of the, okay, DOL is the most common way of connecting an industrial motor called direct online. This direct online is not the internet online. It means that it's connected directly to the three-phase. Okay, direct connect to the three-phase. Okay, so what happens is that when you start, right, in rush current very high, no? As the motor rotate, then the current will reduce in time. Okay, so yeah, and then of course for the other way of connection called star delta, which is not commonly used. Okay, the other one, of course, we look at the soft starter. Okay, the moment you start, the current actually very low, and it slowly, maybe this one it operate at pi/2 lah, 90 degree. Okay, and slowly it become pi/3, 4, 5, 6 until pi/10 until normal. Then it will operate like that. So let's say if your what we call your protection curve lah, usually is something like that, right? Okay, so you will not trip your circuit breaker. Okay, so you can see that application, all right, water pump. This is a high water pump. Okay, we have a fan. This is not our house fan, it's an industry fan. Okay, compressor, okay, and also the conveyor belt for the manufacturing plant. So commonly, the moment you turn on the conveyor belt, right, conveyor actually carry like, the one that used in airport, to carry the luggage. Each luggage, some is 20 kg. And this type of conveyor belt, right, they actually use a very high power motor. The problem is that the moment you start, right, and imagine in airport, you don't start the conveyor, one by one. There are so many gates there. Usually you start, boom, scarly goods, you start 10 conveyor at the same time. Okay, you will have a very high inrush current, overheat the cable, tripping the thing. So of course, one of the solutions is that they tell the guy, you don't turn on the conveyor all the same time. You turn on every two like that. This is one of the way, cheap way. I mean, and the real solution is that you put soft starter for every conveyor. It start at the same time, it won't trip, it gives a soft start. Okay, meaning that it start at the lowest voltage, and that means, in other words, you won't use this to operate a motor like 1 hour in this waveform. No, it's for the soft starting purposes. So don't get me wrong, for three-phase application. All right, single phase, you can use it to turn on your LED light, 24 hours, no problem. All right, so different application. Okay, heating device, I'm not so sure. Magnet, yes. Those, the crane machine that will have the magnet to suck up the metal scrap. You can use that. So it really depends on application. But the most common application is a soft starter. All right. So soft starter, this is how it works. You see, this is from the manual itself. You can see the three-phase come in, right? You can see these are the thyristor. One set, all three-phase. And of course, they always has a bypass switch. If thing doesn't work out, you bypass. Straight away, it becomes direct online. Okay, direct online means that this is a bypass switch. Straight away connect to three-phase without any control. So another configuration is that, you will have another set of breaker here. Usually you will have a fuse here for protection purposes. Okay, and then this is a soft starter and this is a bypass switch. These are all industrial drawing. It's not from textbook. That means this is the real industrial application of a three-phase, what we call this controller. Okay, so I think we are done about AC soft starter. Cyclo converter, okay, we will do that in the next class. See another type of AC controller already. So up to this point, any questions? Hello, guys? You're still there?
Yeah.
Oh, okay, good. All right, so so then we are done with the AC controller that will control the magnitude, okay, of the AC. All right. So I also show the real application, okay, commonly used in this. If one day you happen to work on this soft starter, right? Okay. When one of the phase is unbalanced, usually one set of these already spoiled. Okay, you can change the part of one of these, okay, and you can design your own soft starter or how long it takes to, the time is actually, it can be very fast or it can be very low. It depends on the size of the motor, okay, how you want it to. Usually for conveyor belt, industry like airport conveyor, the one that you collect your luggage also, wow, the moment you turn on, I tell you, high inrush current is coming in. If you have any experience on doing that, I almost can be certain and guarantee that they put the soft starter there to actually, to make sure the airport operate properly. Okay, Okay, so like I say, if you have time, please do that at home. Do this at home, okay, so that you can play around with it. Drawing is very, very important, okay. I don't expect you to draw this complete thing in your final exam. If I ask you to illustrate the drawing, please, at least know how to draw this, okay. The number here is not so important. As long as you can draw the three set here, things should be fine. Okay, similarly for, this single phase. Okay, so if you don't have any questions, okay, I think we can end the class today. Okay. Okay, so no question. Just end the class. Thank you.